So what I have is I have a x which has a distribution function f which belongs to a family P. What I am given is a G, a group of transformations. So before that, suppose my chi is the sample space. Of course, this would be a subset of Rn, the n-dimensional Euclidean space. You can take it to be Rn also, doesn't matter. So G is a group of transformations. One and on to. From chi to chi. So as I said, my first step is to say that P is invariant under this group of transformation G. So the definition is P is invariant, P is said to be invariant. So my set of distributions under this group of transformation which is given to us if for every G belonging to G, that means if I take any transformation in this G, there exists a G bar which is again, so there exists a G bar such that if x has a distribution function f, then y is equal to gx has a distribution function g bar of f. So what it says is, if you apply any g to x, I again get a distribution g bar f which is in P. So if you apply transformation, keep on applying transformation g on x, the distributions which you get are again in P. So I say that such a family of distributions is invariant under G. Now note that each G over here gives rise to G bar over here. So I can talk about collection of all those G bar, collection of all such G bars which correspond to different G's in G. So this group of transformations give me another set of transformations which I am denoting by G bar, because for every small g there is a G bar, and where this G bar is acting on P, because I am talking about G bar of f. So the question is, this is certainly a set of transformations. What can I say about this set of transformations? One can easily prove that this is a group of, so this itself is a group. From theta or from P to P, because G bar acts on f which is an element of P. So one can easily prove this. Now I said, so that means I am saying if I am applying a transformation I remain in the same P. Now I can talk about my loss function to be invariant. So before that, let us try to understand this. If P is invariant under G, let us try to see what does probability when x has f. So Pf would stand for probability measure when X has distribution function f. So this is a probability measure under distribution function f. And my x is a generic random variable. So the better way to write down would be probability measure when f is the true probability measure. True distribution function. Or in other words, it is a probability measure generated by distribution function f. So let us look at what is the probability P of f gx belongs to A. Now this x is a generic random variable. The original x, the data. So what does this say? What is the probability that g of x is in A when my data is coming from f? But I know that if our data is coming from f, then gx has the same distribution function as g bar of f. So this would be same as the probability that x belongs to A as if x has a distribution function g bar of f. So this is same as P of g bar of f that x belongs to A. In other words, if you have to write down everything in terms of expectation, E of f of gx, which is nothing but expectation under the assumption that x has a distribution function f. But when I know that x has a distribution function f, g of x has a distribution function g bar of f. So this is same as E of g bar of f x. Right? So you can keep changing. So these are two small observations. Now I can talk about what do you mean by, if you want to see one example, let us look at P as normal theta 1, where theta is in R. I consider my G as GC, C is in R, and what is my GCX? X plus C. Now note that if x has a normal theta 1, this implies that x plus c would have normal theta plus c, and again variance S1. So it is again of this form, variance remains the same, theta becomes theta plus c, but as a family, if theta is in R, because that is where my family was, theta plus c is also in R for any c. So I still remain in the same family P. This itself belongs to P. So what do we conclude over here? We conclude that P is invariant under this additive group of transformations. Now let us look at one set of transformations under which this P is not invariant. Now if you replace this G by multiplicative group, G as GC, C let us say greater than 0, and GCX is same as CX. Is this family invariant under this multiplicative group? The answer is no. Why? Because if x is normal theta 1, this implies that c times x is normal c square theta square, normal c theta, and variance as c square. Is this family same as this? No. Although c theta would be again in real line, but the variances have changed. So the variance from 1, it has become c square. So I do not remain in the same family, because that was a normal theta 1 family for some theta belonging to R. What is this family? This is again normal C theta, you can denote by eta, normal eta C square family for some eta belonging to R, and C square, as you are varying, C square is not 1. So the two are different. So here I would say that P is not invariant under this group of transformations. So this was a definition of a P being invariant under a group of transformations. Now, the second step I had said, I'll talk about when a loss function is invariant. So, loss function LFA or L theta A is said to be invariant under same group of transformation G, which was defined on the sample space. If what happens? I'm saying the loss in the two problems will remain same. Here I was estimating F, there I was estimating G bar F. So that means for any xn in the first problem, there is an equivalent xn in the second problem. There exists a star belonging to A. The two xn spaces are same in the two problems, so there exists another A star in A, such that what happens? LFA, which was the loss in the first problem, is same as L in the second problem. F has become G bar F, and there is some different xn which gives me the same loss. And this should happen for every F belonging to P. So that means there is a correspondence of, there is an invariance of a loss function in the two problems. So this is a definition of a loss being invariant. And I would say a decision problem is, or an estimation problem is invariant if P is invariant as well as loss function is invariant. And estimation problem PAL or theta AL is said to be invariant under G if what happens? First, P is invariant. Second thing is my loss is invariant. Loss function LFA is so what does this say? So now how should we proceed? So I have a situation where my decision problem is invariant. Now if my decision problem is invariant, I should apply the principle of invariance. That means the two xn's should correspond, and I should use the same decision rule. So based on the discussion which we had in the beginning of this lecture, a decision rule or an estimator delta is said to be invariant under G if delta of taking an xn in set A under the first problem when I am observing x should be same as probability of taking xn in the xn of first problems have corresponded to the xn g tilde is. So this is same as g tilde a, and the observation in the second problem has become gx. So this is what should happen for every so if corresponding to delta dot x, I have random variable yx. So this is equivalent to saying that this is what this comes from the principle of invariance from the last example which we saw. So these are very natural conditions. So which is same as saying that probability that yx belongs to A, because yx is the random variable corresponding to this probability measure delta. Same delta, now gx is given. So this is same as probability that y of gx belongs to g tilde I, which is same as probability that, so you can write down this as PR stands for probability. This same as probability that g tilde inverse y of gx belongs to A. Inverse is not a problem because G is a group of transformations, so existence of inverse is always guaranteed. I'm just repeating whatever I did before. So what does this is? Probability of taking yx taking set in A is same as probability of G tilde inverse y gx taking value in the set A. And this should happen for every A. So what does that mean? That means this random variable and this random variable have the same distribution. So that means yx has same distribution is same as g tilde inverse now g tilde A corresponds to the xn A. Now here I had denoted this A star corresponding to A. So this A star I can denote this by g tilde I, right? Because A star is the xn in the second problem which corresponds to the xn of the first problem. So for every A there exists a A star, right? Which of course would depend on what my G is over here. So this is equivalent to saying that g tilde yx has the same distribution as y of gx, which makes intuitively a perfect sense, because what is a y of gx? This is a random variable for the second problem. It will have a certain distribution. Yx is nothing but a random variable in the first problem. It says if you have to take the xn of the second problem, you apply g tilde, because the xn in the second problem corresponding to A is g tilde I. So this is the xn in the second problem, and if you have to transform the xn of the first problem into the second problem xn, then this is g tilde of yx. Yx was the xn in the first problem when x is observed. You transform it to the xn in the second problem. An equivalent thing over there is g tilde of yx, because A star corresponds to the xn A, and A star I am denoting by g tilde I. Now note that if my estimator was non-randomized, then yx is degenerate. In fact, yx itself I can call as a delta x, which is an xn itself. So non-randomized estimator delta is invariant. Because what is a non-randomized estimator? I have said non-randomized estimator, there is no further randomization, you directly get the xn based on x. So delta x itself is an element of A. Or you can say that delta x is the point where my random variable yx is degenerate. So in this case delta would be invariant under what condition? So yx is same as, so that means g tilde of delta x is same as delta of gx. So this gives you the problem of invariant decision rules. So my principle of invariance says that I should restrict only to invariant decision rules. So let's denote di, the class of invariant rules, estimators. Actually, I'm repeatedly using decision rules because in general decision problem, of which estimation is a particular case, rules are called decision rules because any rule which tells you to how to take decisions is called a decision rule. So class of invariant estimators. So invariance principle suggests that we restrict, we consider only invariant estimators. So now the issue arises, can I find a best estimator? Can I find a best invariant estimator? So best invariant estimator is the one which minimizes the risk for every delta, for every f. So the question is, does the best invariant rule exist? That is, does there exist a decision rule delta naught in di whose risk is the smallest for every parametric configurations? What I am asking is, can I find an estimator delta naught in di such that for every any other delta in d, for any other estimator or for any other invariant estimator, r delta naught f is always less than or equal to r delta of f for every f. Now note that if my class of estimators was not di, it was the class of all estimators, such a thing is not possible, because we saw last time that there are these constant estimators which always minimize the risk at a single point. But now I have restricted my class of estimators the way we restricted our class of estimators by imposing the criteria of unbiasedness. And we saw that if you impose the criteria of unbiasedness, there is a possibility that I may get the best estimator. So the same issue we are faced over here, that whether can I get a best invariant rule. Now, answer to this would be easier if we prove the following result. So suppose delta belongs to di. So delta is any invariant estimator. Then r delta f, that means risk of delta at point f, would be same as risk of delta at point g bar f. Then for every now this is true for randomized, non-randomized, all kind of estimators. So let's prove this for the most general case, which is the case of non-randomized estimators. Now non-randomized estimators, the randomization is taking at two places. First, after observing the x, the randomization is through the random variable yx, which has a probability measure delta dot given x. And then the randomization with respect to x. So that means first let us try to find the average loss at the first stage. So let us try to see what is L star delta f x. Let me try to see if I'm using the correct notations. Yeah. So this is so this is the average loss after the first randomization. What is my loss function? My loss function is LFA. So this is nothing but expected value of L of f of y of x. Expected under. So this expectation is respect to this random variable yx, and this, let me put it as yx. What is R delta f? R delta f is the randomization of this. Now randomization is taking respect to distribution function, distribution of x. So this same as EF. That means when x has a distribution function f, L star delta f x, which is nothing but E of f L of f of yx. Okay. So now let's look at what is R delta G bar f. But before that, let us try to see my delta is invariant. What does that mean? Delta corresponds to random variable yx. That means the two actions should correspond. The action, if I convert the action of the first problem, it becomes G tilde of yx. And that should be same as y of gx, because these are action in the second problem. Second, you're observing gx and using the same decision rule y, or the same random variable y. So what do you get? So R delta f is nothing but EF L of f G tilde inverse So everywhere I am assuming in an invariant, so here also the assumption is, so the assumption here is problem is invariant. So this is an assumption. So your decision or estimation problem is invariant under G. And delta is a invariant decision rule, and this is what it happens. This is same as E of. Now note that this was when generic random variable x has a distribution function f. Now note that when x has a distribution function f, gx has a distribution function g bar f. So I can write down this as g bar of f, and then L f g tilde inverse y of x. Now I use the fact that my loss function is invariant. Loss is invariant, what does that mean? LF of A should be same as L of G bar F and G tilde I. So this is same as E of G bar F, that remains as it is. L of G bar F and G tilde of y of x. Why? Because loss is decision problem is invariant, so your loss is invariant, so that means LF of A is same as loss. In estimating, in second problem you are estimating G bar F, and second estimation problem, the action corresponding to A is nothing but G tilde I. This is what happens, because loss is invariant. So this is same as E of G bar of F L of g bar of f and yx. Just compare this with this. It is exactly the same except that f has changed to g bar f. So this is the risk of yx remains the same. So this is same as risk of delta at the point g bar f. So that means if I have 2 points f1 and f2 and they are related through some g bar, then they would have a same risk because r delta f is same as r delta of g bar of f. So I write down this as a remark. Suppose delta belongs to di and f1 and f2 belongs to p are such that f1 is same as g bar of f2 for some g bar. Then what can you say about r delta f2? R delta f2, because delta is invariant, would be same as r delta of g bar f2. And g bar f2 is same as g bar f, so r delta f1. So that means they will have the same risk. Now this has a very important consequence, which says that if your family of distributions P is such that any two distributions in P are related through some g bar, then the risk function would always be constant. So another remark, if P is such that for every two elements f1 and f2 in P, f1 is same as g bar of f2 for some g bar belongs to g bar, then r delta f for all of them would be same, because r delta f1 is same as r delta of g bar of f2, and any two f's are related through g bar. So that means the risk of any two of them would be constant. It would be the same. So, or in other words, r delta f would be constant for every f belonging to P. So, or in other words, it does not depend on P. All of them would have a same. This should always be constant. Yeah. So what it says? It says if you consider any invariant rule, its risk will not depend on f. And if you recall why we were not able to find the best estimator, because my risk function depends on f or theta. And it is not possible to minimize r delta f or r delta theta for every f or every theta. But now it no longer depends on f or theta. So what I have to do? There are few constants. And I look at all invariant rules whose risk is constant. I look at the one which has the smallest constant risk, and that may be possible. So may be possible to get best invariant, especially in situations where my P says that any two elements of P are related through some g bar. In such situations, it may be possible to get the best invariant decision rule. Now, if such a thing happens, we say that g bar acts transitively on P. Or in other words, if my group of transformation is such that for any two elements in P, there is a G bar such that the two elements of P are related through this G bar, then we say that G bar acts transitively on P. So what it suggests is if G bar acts on transitively on P, then the risk function of any invariant decision rule is constant. And then I'm no longer dealing with the problem of minimizing a constant for every theta. I'm just trying to find an estimator for which this constant is minimum. You see, different deltas would have a different constant. And then it may be possible to find an estimator which has